Okay, in this video, we're going to talk about sections 6.2 and 6.3 because 6.2 is just playing with numbers and 6.3 is application. So basically, that means turning English into mathematics and then basically doing what we did in 6.2. Okay, so 6.2, we learn another way to solve a system of equations. In 6.1, you learned elimination, and the tenets of elimination will turn into this thing called the Gauss-Jordan method. So before we get to the actual method itself, we have some terms we have to get through. But let's talk about what was happening in the elimination method. So basically, you multiplied one or both equations by a non-zero number to eliminate variables. And then once you got down to one variable, you back substituted to get the eliminated variables. That's basically a summary of what elimination is doing. In this thing called the Gauss-Jordan method, you are allowed to do three operations. As you see on the screen there, they're called your elementary row operations. Let me make that bigger. Oops. Boop. Nope. Boop. And in your elementary row operations, you'll be working with a thing called a matrix, which we'll define in a second. Matrix is just a bunch of rows and columns. And these are the three things you are allowed to do. You are allowed to interchange any two rows. That is just like in the elimination method. If you wrote the first equation second, you didn't change the answer. You just changed what it looked like. You're allowed to multiply an equation by a non-zero number. That's the same thing as multiplying a row by a non-zero number. So if I had the equation 3x equals 6, I could multiply both sides by 1/3 to get x equals 2. I did not change what the solution was. I just changed what the equation looked like. And 3 is basically what you did with elimination. You can multiply an equation by a non-zero number and add that to another equation. The purpose for that in the elimination method was to make these variables go away. Well, these three things were built for equations. I accidentally said row earlier, but it's the same idea. These three things were built for equations, but we can make this into what's called a matrix. So for every system of equations, there is a corresponding matrix. Let's formally define a matrix. Now, before we get to it, it's an ugly definition. So if you remember earlier on in the semester, I told you, when we write down what a polynomial is, you'll hate it, but there's something worse. Well, this is the something worse. So sit tight. I'm about to hit the button. In 3, 2, I lied. I just hit the button. So a matrix is a rectangular array of numbers of the form blah. Look at all that stuff. It's beautiful. Where each a sub I comma j is a real number called an entry or an element of the matrix. M is the number of rows and n is the number of columns. The size or dimension of the matrix is given by m by n. All right, pause the video if you have to. There's a lot to unpack here. All right, so what's happening here is these are little subscripts here, and these subscripts tell you the row, comma, the column, that the number is in. So a sub 2, 3 means the 2, second row, the 3 means the third column. 1, 2 means first row, second column. So it's always row by column, always, always, always. So m is the number of rows, n is the number of columns. That's why these all start with an m comma something, and these all end with a comma n. So let's just make up a matrix. I'm just making up some numbers here. So for instance, the 8 is in which row? You would say the first row. In which column? You would say the third column. So the 8 is the 1, 3 entry. The 6 is in which row? It's in the second row. It's in which column? It's in the first column. So the 6 is the 2, 1 entry. How many total rows do we have? We have 2 rows. Remember, rows go across. By how many columns do we have? We have 4 columns. So the size or the dimensions of the matrix is 2 by 4. Okay. So for any system of equations, you can create what is called an augmented matrix. So augment, what does it mean to augment something? It means to make bigger. So for instance, if you ever do music theory, if you augment a note, like if you augment C, you would say C sharp. So it's just the note directly to the right of it, whether it be black or it be white, it's the one to the right of it. So that means what it means to augment, to make bigger. So for instance, if I had the system, just making this up, 2x plus 3y equals 9, and x minus 4y equals 8, we can turn this into a corresponding system. Since we have 2 equations, we would need 2 rows. And since we have 2 variables and constants, we would need 3 columns. So we would have an x column, a y column, and a constant column. And typically for an augmented matrix, you put a little vertical line here, and that tells you that you put a matrix next to another matrix, so they're now one matrix. So that's what it means to augment. Marsh really loves that toy. So the purpose of matrices is now it's a positional system. It doesn't matter. We don't need to write x and y's over and over and over again. Just make sure you keep them in the right position. So if I write something in the first column, that means those are coefficients for x. If I write something in the second column, those are coefficients for y. And if I write something in the last column, that's a constant. So the equation 2x plus 3y equals 9 becomes the row, if I can find my cursor, 2, 3, 9. And the second equation, x minus y, oh, that's a y. It really is a sloppy y. It looks like a 4. X minus y equals 8 becomes the row 1, negative 1, 8. So we don't need the variables anymore. The position tells us what the variables are. So that's comment number 1. Comment number 2 is in the previous section, we would solve the system. I don't know what these numbers are off the top of my head. I really don't want to do the math. It's so early. I didn't have my coffee. So let's just say x would equal a number and y would equal a number. Ow, no! Ow, no! Ow! Everything's fine. Where's my cursor? There it is. Okay. Now, the reason I wrote it this way is so we can mimic this. So our goal in 6.1 was to get x equaling a number and y equaling a number. Well, let's see what that looks like now as a matrix. So x equals number means, well, how many x's are there? There's 1 x. There's a 1 right here. How many y's are there? There's 0 y. So we would put a 0 here. And then we have a number. And the second row would be we have no x's, but we have 1 y, and that equals another number. So the way we went from the top to the bottom in the system over here was elimination. The way we go from the first matrix to the second matrix is this thing called the Gauss-Jordan method. Gauss, G-A-U-S-S, Jordan, and then method. There's technically a hyphen here because it's 2 different. I think that's 2 different guys. I don't know. I didn't ask. Okay. So our goal is to turn our initial matrix, the 2, 3, 9, 1, negative 1, 8, into the matrix 1, 0, number, 0, 1, number. And it's this thing called the Gauss-Jordan method. Well, the way you do that is by using these elementary row operations. So in numbers 1, 2, and 3, instead of the word equation, you could replace it with the word row because the same rules apply. So let's see what that would look like here. I should really just go back, but I'm way too lazy. What did I say? 2, 3, 9, 1, negative 1, 8. And then over here, I'm going to write goal. Okay. Now, here's the bad thing. In Chapter 6, we have guidelines. We do not have an algorithm, meaning that we have rules of what we are allowed to do, namely 1, 2, and 3 on this screen, but there are no rules in what order they have to go in, meaning there's no algorithm. There's no step 1, step 2, step 3. In Chapter 7, we will have both rules and an algorithm. So it does get better later on. So that's the good news. So here are my, here's what I'm going to go by. So the goal is to take our beginning matrix and turn it into our goal matrix in the bottom right there. If we are able to do that, then we can read across x equals number, y equals number. Great. So my rule is start with the leftmost column. Make your 1 and then make your 0. I'll say that again. Start with the leftmost column. Make your 1 and then make your 0. So for instance, here is the leftmost column, which needs to match this leftmost column. And so, oh my God, I just touched my face! Anyways, so then in that column, this 2 needs to become a 1. Let's do that first. Let's talk about all 3 of these ways that this could happen. 1, interchange the 2 rows. That means I write the second row first and the first row second. If I were to do that, if I were to swap these 2 rows, then notice that would put a 1 in the 1, 1 position. So that would work for us. So let's consider that one. Let's think about that one. Number 2, let me undo that real quick because I don't want that to get in the way. Where's my eraser? Why is this so hard to use? Number 2, I could multiply a row by a non-zero number. Well, if I'm at a 2 and I want to get a 1, I could multiply everything by a half. That's totally fine. With that, though, that would create a fraction here and a fraction here. You want to try to avoid fractions if you can. Later on, we're going to learn how to do all this in the calculator. In fact, that's one of the videos coming up for you guys. So there should already teach you how to use the calculator. So please pay attention to that one. So since we're doing the first one by hand here, let's try to avoid fractions. But if you want to make ones, the second row operation can be used. Number 3, multiply one equation by a non-zero number and add it to another equation. Well, if I multiply the second row by -1 and I added that new row to row 1, -1 plus 2 makes 1. So I could use all 3 of these operations to create a 0 if I so choose. However, let's do the easiest one, and the easiest one is to interchange the 2 rows. The notation we use, and yes, you get to use it. I don't want to hear it. I can hear it. I don't want to hear it. Is you would say R1, the first row, double arrow, switches with R2, the second row. The first row switches with the second row. So now the new first row is 1, -1, 8, and the new second row is 2, 3, 9. Notice we got a 1 where we need it to be in the first column. So we are 25% done. Mazel tov. But, as I said, start with the leftmost column, make your 1, and then make your 0. So now this 0, oh, I didn't pick a good color. I'm sorry, this 2 needs to become a 0. The operation that always makes zeros, notice I'm using my write this down voice without touching my face this time. The operation that always makes zeros is the third one. Boop. So this is basically your elimination method. Did my line go away here? I thought I had one. So use the 1 that you just created. 1 times what plus 2 makes 0. 1 times what plus 2 makes 0. Hopefully you say -2. So if you multiply the second row by -2, that's what this says in English, multiply the second row by -2, and add that to the first row, that will create the new first row. Marsha is going to town on that toy. Okay. Since we're doing this by hand, let's write out everything. Again, pretty soon you'll learn how to do this all on the calculator. So just pay attention to that. It goes much faster on the calculator, by the way. So off to this. Oh, kids, I made a mistake. I think I said things right, but I didn't write it down correctly. We're multiplying the first row by -2 and adding the result to the second row, and that makes the new second row. Haha, good thing I'm not in class right now. You'd be all upset. Freeze frame. All right, good. So off to the side, let's write down what -2 times row 1 looks like. So we're taking this row here and just writing down what that looks like times -2. So 1 times -2 is -2. -1 times -2 is +2. 8 times -2 is -16. Now we take these three numbers, which is this guy right here, and we're going to add it to row 2. So 2 plus -2 makes 0. 3 plus 2 makes 5. Ooh. And I'll draw a triangle. 9 and -16 makes -7. So again, we multiplied the first row by -2. That's below that big arrow there. We took those three numbers and added it to the second row. That's the circle, square, triangle thing. And that created the new second row, 0, 5, -7. Now I'm going to write in the old row 1, because that technically did not change. The multiplying by -2 is all side work. Okay, so notice now the first column is done. We got a 1 and then we got a 0. Huzzah! Now, once the first column is done, we move on to the second column. Oh, I picked the wrong color again. So now we want the second column, that does not look any different from the yellow, to match the second column in our goal. Maybe it's a little bit better. So again, make your 1 and then make your 0. We're not going to do all three. We're not going to do the entire problem here. The whole point of this was you to get used to what the operations are doing. So make your 1 first. So this 5 needs to become a 1. As stated earlier, the second operation can be used to make 1s. 5 times what equals 1? Hopefully you would say 1/5. So 1/5 times row 2 makes row 2. So off to the side, 1/5 times 0 is, I'm not off to the side. Put this right into your matrix. 1/5 times 0 is 0. 1/5 times 5 is 1. And 1/5 times -7 is -7/5. We did not modify the first row, so I'm going to put that in. You know what? We're right here. We might as well finish it. So notice we got our 1 in the 2, 2 entry. That's great. And now we need a 0 in the 1, 2 entry. Well, we have a 1 here. We have a -1 here. So notice if I say add row 2 to row 1, and that will create the new row 1, then we're good to go. I don't need to do anything off to the side here because I'm not multiplying the second row by anything special there. So 0 plus 1 makes 1. 1 and -1 makes 0. -7/5 plus 8, well, 8 is 40/5, so 40/5 minus 7/5 is 35/5. And then I'll just copy in the second row. So now reading across, remember this is the x column, this is the y column, this is the constant. This says 1x is 33/5, so x is 33/5. And 1y is -7/5. Hooray! So you might be like, Mike, that took very little time compared to the elimination method. Thank you for teaching me. And I'll say you are welcome, student. Yeah, granted, for a 2-variable system, this is not ideal. We are going to be getting into much larger systems, like 4x9, 5x10s. So this is where we're headed. That's why we're doing this now. So yeah, for smaller systems, I would probably just do elimination. But this matrix stuff, Gauss-Jordan, is much better for larger systems. Okay, so you have a slew of examples to go. In fact, I did not load up my web page. Let's see. Boop. Oh, I clicked on the wrong thing. All right, click in here. I need you to watch videos. Uh, 70. Yeah, 70, 71. That should put you in 6-2. And then 72, 73. Should put you in 6. I'm sorry. 70, 71 is 6-2. 72, 73 is 6-3. Video number 72 uses the calculator.
All right.
So it's a longer video because I go through all the steps on how to do the elementary row operations in the calculator. Watch that thing a couple times if you need to, because there's a lot going on there. I'm not saying you have to use your calculator, but your life will be a lot easier if you did. Okay. And I'm just looking at video number 72. Oh, I'm sorry, video number 73. I apologize. Okay, so in video 73, I talk about setting up the words into a system of equations, but I don't show solving them, but I do show the answers. So please, in that video, which again is basically 6.3. I want you to try to solve them after you have them set up. You can use elimination, but I prefer that you got used to your calculator. If you have any issues with those, shoot me a message, and we'll go from there. All right, so that's again 6263. Laters.